So far, we've discussed rotational motion, and we've seen the rotational equivalent of some quantities. For example, torque in place of force, angular velocity in case of linear velocity, angular acceleration in place of acceleration, moment of inertia in place of mass, rotational kinetic energy in place of energy, and so on. And we've also seen that these rotational quantities are related in the same way that their linear equivalents are. The quantity linear momentum also has a rotational equivalent, and it's called angular momentum. For an object rotating about a fixed axis, the angular momentum is given by the object's moment of inertia about the axis multiplied by its angular velocity. The SI unit for linear momentum is kg meter square per second. We know that in the translational case, Newton's second law can be written not only in terms of acceleration, but more generally in terms of momentum as the net force acting on an object equals the rate of change of linear momentum of the object with respect to time. In a similar way, we can write the rotational equivalent of Newton's second law, not only in terms of angular acceleration, but in terms of angular momentum. And we can write it as the net torque acting on a rotating body is equal to the rate of change of its angular momentum with respect to time. We can show the relationship between the two expressions of angular momentum. Since the angular momentum is equal to the moment of inertia multiplied by the angular velocity, we can write the net torque as the derivative of the moment of inertia multiplied by the angular velocity with respect to time. And in the case where the object rotates about the same axis throughout, the moment of inertia of the object is constant. So we can say the net torque equals the moment of inertia multiplied by the derivative of the angular velocity with respect to time, which is the angular acceleration of the object. Angular momentum is a conserved quantity, and we can see that when there is no net torque on the object, the change in angular momentum is zero, and so angular momentum remains constant. This is expressed by the law of conservation of angular momentum, which states that the total angular momentum of a rotating body remains constant if the net torque acting on it is equal to zero. Let's solve a few problems so that we can apply what we learned about angular momentum. We'll start with something simple. Say we have a ball of mass 0.3 kilograms revolving on the end of a thin string in a circle of radius 1.2 meters at an angular speed of 10.4 radians per second. If we wanted to find its angular momentum, we would simply multiply its moment of inertia by its angular velocity. And since the ball as a whole is rotating about the central axis, we can take it as a particle which is rotating. So its moment of inertia would be expressed as the moment of inertia of a particle, which is its mass multiplied by the square of its radius, or the square of its distance from the center of rotation. And so for the ball, its moment of inertia would be equal to 0.3, which is its mass, multiplied by 1.2 squared, which gives us 0.432 kg meter squared. So its angular momentum will be 0.432 multiplied by 10.4, which gives us 4.49 kg meter squared per second. Let's move on to something a little more complicated. Assume we have a person of mass 75 kilograms standing at the center of a rotating platform having radius 3 meters and a moment of inertia of 820 kg meter squared. This platform rotates without friction with an angular velocity of 0.95 radians per second. We know the angular velocity of this rotating platform, but suppose the person walks from the center of the rotating platform to the edge. Would the angular velocity of the system remain the same, or would it change? We can use the principle of conservation of angular momentum to determine whether or not the angular velocity will change, and if it does change, what the angular velocity of the system will be when this person is at the edge of the platform. No net torque acts on this system, and we know that when the net torque on the rotating body is equal to 0, its angular momentum remains constant. So the angular momentum when the person is at the center of the platform is the same as when they are at the edge of the platform. We can write this as I1 omega 1 equals I2 omega 2, where I1 is the moment of inertia of the system in the first instance when the person is at the center of the platform, and omega 1 is the corresponding angular velocity. I2 is the moment of inertia of the system when they are at the edge of the platform, and omega 2 is the corresponding angular velocity. In any of the cases, we can take the moment of inertia of the entire system as the sum of the moments of inertia of the person and the platform about the axis. We've been given the moment of inertia of the platform as 820 kg squared. For the person, we'll assume that the system is a lot larger so that we can calculate their moment of inertia as we would a point mass or particle. So the moment of inertia of the person can be expressed as its mass multiplied by the square of their distance from the center of rotation. When this person is right at the center, their distance from the center would be 0, and so their moment of inertia would in turn be equal to 0. And so we can write I1 as 820 plus 0, which equals 820 kg squared. When at the edge, their moment of inertia would be equal to 75 times 3 squared, which equals 675 kg squared. And so we can write I2 as 820 plus 675, which equals 1495 kg squared. We know omega 1 to be 0.95 radians per second. So plugging our values into our equation of conservation of angular momentum, we can solve for omega 2. And we obtain omega 2 to be 0.52 radians per second. So we see that our angular velocity does in fact change. But how about the rotational kinetic energy of the system? Let's compare the initial and final rotational kinetic energies of the system. So in the first instance, our kinetic energy is equal to half I1 omega 1 squared, which gives half times 820 times 0.95 squared, which is equal to 370 joules approximately. In the final instance, when the person is at the edge of the platform, our kinetic energy is given as half I2 omega 2 squared, which gives half times 1495 times 0.52 squared, which is approximately 202 joules. This seems like a weird result to obtain because it implies that there has been a decrease in rotational kinetic energy of the system. But the system didn't do work in resisting any opposing torque, and there was also no resistance due to friction, since we know the platform experiences a frictionless rotation. And from our conservation of mechanical energy, we know that the mechanical energy of a system remains the same if no work is done on it or if it doesn't do any external work. So how does its kinetic energy decrease? We can explain this by considering the centripetal force experienced by the person. Once they start to move from the center, their angular velocity is no longer 0, and they experience a centripetal force directed towards the center of rotation. Moving from the center of rotation to the edge of the platform is in opposition to this force, and so work is done against this force by the person in moving from the center to the edge. And so the quantity of work done accounts for the decrease in kinetic energy of the system.